More than 80% of Earth's oceans remain unmapped, unobserved, and unexplored, a submerged territory so vast that it exceeds the total surface area of Mars. This is a staggering fact that defies intuition. Humankind has charted the surfaces of distant planets, landed rovers on the red dunes of an alien world, and mapped nearly every square kilometer of the lunar far side. Yet the waters that cover 71% of our own planet hold secrets that have never been witnessed by any conscious eye. The ocean is not a shallow puddle to be waded through. It is a three-dimensional universe layered like an immense cake, descending into darkness that has no equivalent on land. This is the story of that descent. It is a journey into the eternal night that swallows light, where pressure would crumple a submarine like paper, and where life has found a way to flourish against all rational expectation. What waits in the crushing darkness below? How does anything survive where the sun's rays never reach, where temperatures hover near freezing, and where food is scarcer than gold? The answers defy imagination. And the deepest point of all, a place called Challenger Deep, waits at the bottom of this void to reveal them. To understand this descent, one must first confront the sheer scale of what remains unknown. The 60% figure often cited by oceanographers accounts for maps drawn from satellite altimetry, which can detect broad features but miss everything beneath a few kilometers of resolution. By these measurements, more than 80% of the global ocean floor remains unmapped at any meaningful detail. We know more about the geology of Venus, behind its thick, toxic clouds, than we do about the abyssal plains that lie only a few kilometers beneath our boat hulls. Every year, scientists lower cameras into these depths and find creatures that were not even theorized to exist, shapes from a fever dream, glowing in the bioluminescent glow of their own bodies. But the ocean is not a uniform void. It is stratified, a series of distinct realms stacked one atop another. The sunlit surface, called the epipelagic zone, extends from the water's skin down to 200 meters. This is where photosynthesis thrives, where coral reefs explode with biodiversity, and where the greatest migration on Earth occurs nightly. Beneath that lies the twilight zone, the mesopelagic, stretching from 200 to 1,000 meters, where light fades into a dim blue glow and creatures pierce the gloom with lights of their own design. Below this is the midnight zone, the bathypelagic, a world of pitch-black silence beginning at 1,000 meters, where blinking lures and dangling teeth patrol waters that have never seen a sunrise. Farther down, past 4,000 meters, spread the abyssal plains, vast, sediment-covered flats that reach across the ocean floor like a desert of frozen mud. Finally, only in the deepest trenches lies the Haddle Zone, found at depths exceeding 6,000 meters. This last realm is not a worldwide layer, but a series of isolated cracks, some carved into the very crust of the Earth. Each transition between these layers marks a dramatic change in pressure, temperature, and light availability. At just 100 meters below the surface, the pressure is roughly 10 times that of the atmosphere at sea level. At the bottom of the Mariana Trench, Approximately 11,000 meters down, the pressure exceeds 8 tons per square inch, the equivalent of a full-grown elephant standing on a thumbnail-sized square of skin. No human can withstand this unprotected. No submarine is built to last forever in such conditions, and yet life exists there. The sunlit surface may produce the bulk of the ocean's biomass, but the deep is where the true extremes test the limits of biological possibility. Creatures in the deep have evolved gelatinous bodies that are merely transparent, not to hide from predators, but because bones and rigid structures would be crushed by the water's immense embrace. The anglerfish has turned a modified dorsal fin into a glowing lure, dangling it like a fishing pole in front of its face to attract prey. The gulper eel can open its mouth wide enough to swallow creatures larger than its own body. Vampire squid, despite their terrifying name, drift through the black waters, wrapping themselves in a cloak of webbed arms, safe in their utter invisibility to any creature that expects to see black in black. None of these wonders, however, compare to the single most astonishing fact about the deep ocean. Less than 5% of its waters have been seen by human eyes. A 19th century explorer would recognize Mars more easily from modern photographs than any scientist would recognize the trenches beneath their own fields of study. And yet, the exploration that has been done has revealed not just strangeness, but beauty, a kind of alien artistry in evolution's design. What follows is the record of that descent. From the chaos of the surface waters, where sunlight powers the engine of life, winding down through the layers where light dies by degrees, past the point of no return into absolute darkness, all the way to the bottom of the world's deepest wound, Challenger Deep itself. At that final point where pressure compresses water until it behaves differently than at the surface, where the temperature hovers near freezing, and where no light has ever reached, explorers have found not emptiness, but a teeming microbial world, a testament to life's stubborn refusal to yield. They have also found plastic bags. They have found pollution, the unmistakable fingerprints of humanity, even at the doorstep of the abyss. The question that drives this descent is twofold. First, what exists in the eternal darkness below? Second, how does life survive where sunlight never reaches? The second question, once thought unanswerable, has been answered by volcanic vents that pump chemical energy into the void, and by a phenomenon called marine snow, a slow drift of organic particles that falls from the upper layers, providing a rain of food to the invisible dwellers below. But these answers raise deeper questions. If life can thrive in crushing pressure and absolute darkness, where else might it thrive? If extremophiles can live on chemical energy from the Earth's interior, perhaps similar organisms exist on Europa's frozen oceans or beneath the methane lakes of Titan. The deep ocean is not just a realm of strange fish and glowing medusas. It is a planetary archive, a regulator of climate, and a reservoir of nutrients that circulate across the entire globe in a slow, majestic dance called the Great Ocean Conveyor. It absorbs heat and carbon dioxide, buffering the planet from rapid changes that would otherwise make the surface uninhabitable. The deeper we descend, the more we realize how interconnected every layer truly is. No creature in the abyss survives in isolation. Each one depends, at some distance, on the energy of the sunlit world above, either directly through marine snow or indirectly through the vertical migrations of billions of organisms that journey daily between light and dark. So the dive begins. At the surface, the water is welcoming, warm, full of life. But within 200 meters, the light begins to fail. At 1,000, there is only blackness. At 4,000, pressure crushes steel. At 11,000, near the very heart of the Earth's crustal machinery, the probe sends back its images, and the answer, utterly unexpected, is that life is everywhere. The descent awaits. Every single breath a human takes draws in oxygen that was, at some point in the deep past, exhaled by the ocean. But more startling is the present tense reality. More than half of all, the oxygen in Earth's atmosphere is produced not by forests, not by jungles, but by microscopic organisms drifting in the sunlit waters of the sea. Phytoplankton, single-celled plants adrift by the trillions, perform a silent photosynthesis beneath the waves that dwarfs the output of every rainforest combined. The very air that fills the lungs of every creature on land has its ultimate origin in this thin, sun-drenched skin of the ocean. Before the descent into eternal darkness can begin, one must understand the engine that powers everything below. The epipelagic zone, extending from the surface down to approximately 200 meters, is where the ocean's story starts. Here, sunlight penetrates with sufficient intensity to drive photosynthesis, and this single fact transforms the surface waters into the most densely populated habitat on the planet. In 1 liter of surface seawater, there can be upwards of 1 million phytoplankton cells, invisible to the naked eye, yet collectively visible from space. When conditions align, nutrients, sunlight, temperature, these organisms bloom across thousands of square kilometers, painting the ocean in swirling green and blue. Patterns that satellites observe from orbit. The mechanics of ocean photosynthesis are deceptively simple. Sunlight strikes the water's surface, and within the first few meters, most of the red and yellow wavelengths are absorbed, leaving only blue and green light to penetrate deeper. This absorption determines the distribution of life. Phytoplankton, containing chlorophyll, capture what remaining light they can and convert it into chemical energy, releasing oxygen as a byproduct. This process has run for over 2 billion years, gradually transforming Earth's atmosphere from a toxic mix of volcanic gases into the breathable air that makes terrestrial life possible. The ocean did not just host life at its surface, it created the conditions for all life that followed on land. The diversity generated by this surface energy is staggering. Around the equator and in warm coastal waters, the sunlit zone hosts coral reefs, often described as the rainforests of the sea. These structures are not rocks, but living organisms, colonies of tiny polyps that secrete calcium carbonate shells and form vast, three-dimensional cities. A single reef system can house thousands of fish species, hundreds of coral types, and an uncounted array of worms, crustaceans, mollusks, and sponges. The Great Barrier Reef alone, stretching over 2,000 kilometers along Australia's eastern coast, is visible from space and supports an estimated 9,000 species, including fish, mollusks, and marine mammals. Each coral polyp harbors symbiotic algae called zooxanthellae, which perform photosynthesis and supply the coral with up to 90% of its energy needs, a partnership that thrives only in shallow sunlit water. Above the reefs and through the open waters, the surface zone is a highway for some of the largest animals ever to have lived. Blue whales, reaching lengths of over 30 meters and weights near 200 tons, migrate thousands of kilometers through these warm surface waters, filter feeding on the dense swarms of krill that bloom where phytoplankton gathers. Humpback whales travel distances that stagger belief, some populations swimming over 8,000 kilometers in a single migration loop between feeding and breeding grounds. These creatures navigate not just by sight but by Earth's magnetic field and by the acoustic properties of the water column, producing songs that travel for hundreds of kilometers through the water, communicating across vast distances in a manner that remains only partially understood. But the sunlit zone is not merely a passive habitat. It is a dynamic, turbulent realm shaped by winds, currents, and temperature gradients. The ocean's surface absorbs solar radiation, warming the upper layers and creating stratification, a layering where warm, light water floats above cooler, denser water. This stratification governs the exchange of gases between ocean and atmosphere. The ocean absorbs carbon dioxide from the sky, dissolving it into the water where phytoplankton eventually incorporate it through photosynthesis. When these organisms die or are consumed, the carbon sinks into deeper layers, a process known as the biological pump, which sequesters carbon for centuries to millennia. The surface zone also drives global weather patterns. Warm waters evaporate, feeding storm systems that distribute heat across the planet. El Niño events, triggered by warming of the tropical Pacific surface waters, can shift weather patterns worldwide, causing droughts in one hemisphere and flooding in another. The sunlit zone is not a unsaid. Sunlit zone is not a first, separate layer, but the thermostat of a connected global system. Within this busy realm, creatures have evolved remarkable strategies for survival. Flying fish launch themselves from the water's surface, gliding for distances over 200 meters to escape predators below. Sailfish are considered some of the fastest marine animals, reportedly reaching speeds above 100 kilometers per hour, slashing through schools of smaller fish with spectacular bursts of acceleration. Sea turtles, some species diving to depths of over 1,000 meters, despite being air breathers, return to the surface to bask in the sunlight, an activity essential to regulating their body temperature. Manta rays with wingspans reaching over 6 meters perform somersault-like barrel rolls in plankton-rich waters, threading the water through their gill plates to harvest microscopic life. The bottom boundary of this sunlit world is not a line on a map, but a gradual fade. As depth increases from around 100 meters downward, sunlight grows dimmer until photosynthesis no longer yields sufficient energy for plant life. This transition zone between 100 and 200 meters hosts the last vestiges of truly sunlit life amidst a deepening blue twilight. Here, fish exhibit darker coloration and larger eyes, adaptations to maximize every available photon. Below 200 meters, photosynthesis becomes mathematically impossible. The energy from the sun's rays that penetrates beyond this point is insufficient for green plants to split water molecules. Life in the twilight zone below must rely on food falling from above or on its own bioluminescence. Yet even as light fades, the surface zone's influence persists. The oxygen produced at the surface dissolves into the ocean and is carried by currents into the greatest depths, providing the very breath of life for the abyssal realm. The sinking of dead plankton and fecal pellets, what scientists call marine snow, feeds creatures living kilometers below. The sunlit zone is not a separate chapter in the ocean story. It is the opening scene, without which nothing below could exist. As the descent begins, the waters turn cooler and darker with every meter. The sun-warmed surface gives way to a trembling blue-lit stillness. Ahead lies the twilight zone, where creatures glow and a new set of rules govern survival. But the sunlit surface, with its dazzling reef cities, its towering whale migrations, and its trillions of invisible, oxygen-making algae, remains the anchor of all ocean life, a realm of motion and abundance that sets the stage for the dark world that follows. Each night, as the sun sinks below the horizon, an invisible exodus begins. From the dark depths below 200 meters, countless millions of creatures rise toward the surface, traveling hundreds of meters through the water column in a coordinated ascent that repeats with the regularity of a heartbeat. This is the largest migration on Earth, dwarfing the movement of any land animal, involving more biomass than all terrestrial migrations combined. By daybreak, these travelers will descend again, retreating to the safety of darkness before the sun's rays can expose them to predators. This daily rhythm, known as vertical migration, defines the sunlit zone's most intimate connection to the world below. The creatures that participate in this journey are surprisingly small. Lanternfish, bristle mouths, krill, and copepods form the bulk of this nightly army, rising to feed on phytoplankton that thrive in the sunlit surface waters. By day, they hide in the twilight depths, their dark bodies and light-sensitive eyes adapted to a world of perpetual dusk. By night, protected by darkness, they ascend to gorge on the ocean's green harvest. Some species travel over 400 meters in a single evening, a journey equivalent to a human climbing a skyscraper before breakfast. Scientists estimate that these vertical migrations transport billions of tons of carbon each year, a churning engine that links the sunlit surface to the abyssal depths. This migration is more than a feeding strategy. It is a vital planetary mechanism. As these creatures rise to feed and then descend to excrete their waste, they carry carbon from the surface down into the deep ocean. This biological pump removes carbon dioxide from the atmosphere, sequestering it in the ocean's interior, where it can remain for centuries. The ocean absorbs roughly 1/4 of all human-caused carbon emissions, making it the planet's largest active carbon sink. The surface zone, by virtue of its sunlight and photosynthesis, is the entry point for this immense carbon cycle that regulates global climate. But the surface zone does more than absorb carbon. It also absorbs heat. The ocean has absorbed over 90% of the excess heat generated by rising greenhouse gas concentrations. The uppermost layers of the ocean have warmed measurably over recent decades, and this warming is not without consequence. Scientists monitoring sea surface temperatures have documented a steady rise, particularly in tropical regions where coral reefs are especially vulnerable. When temperatures exceed certain thresholds, corals expel their symbiotic algae in a stress response known as bleaching. Without the zooxanthellae that provide up to 90% of their energy, corals turn white and begin to starve. Widespread bleaching events, occurring with increasing frequency across the Great Barrier Reef and other reef systems worldwide, have transformed vibrant underwater cities into ghostly graveyards. The effects of warming are not limited to corals. Phytoplankton, the microscopic engines of oxygen production and carbon capture, are also sensitive to temperature changes. Warmer waters increase stratification, forming a stronger barrier that prevents nutrient-rich deep water from rising to the surface. In nutrient-limited regions, this can reduce phytoplankton productivity, undermining the base of the entire marine food web. Some studies suggest that global phytoplankton populations have declined by a significant margin over the past century, a shift with cascading consequences for every creature that depends on the ocean's bounty. The sunlit zone also faces the threat of acidification. As the ocean absorbs more carbon dioxide, the resulting chemical reactions lower the water's pH, making it more acidic. This acidification interferes with the ability of shell-forming organisms, including corals, mollusks, and certain plankton, to build their calcium carbonate structures. For creatures living in the sunlit zone, this means weaker shells, slower growth, and reduced survival rates. The impacts ripple upward through the food chain, affecting everything from tiny pteropods to the great whales that feed on them. Despite these changes, the sunlit zone remains one of the most resilient and dynamic environments on Earth. Its waters teem with life in staggering abundance, a visually overwhelming chaos of color and motion. Massive schools of sardines and anchovies pulse through the water like single shimmering organisms. Dolphin pods slice through the surface, their streamlined bodies exploding into the air with breathtaking grace. Seabirds wheel overhead, diving to snatch fish from just beneath the waves in an aerodynamic display perfected over millions of years. The surface of the ocean is a boundary between two worlds, and both sides are rich with activity. At the edge of the continental shelf, where the sea floor drops away into the deep ocean basin, the sunlit zone's influence extends in a thin band above an immense volume of dark water. Beyond this point, the sunlit zone is restricted to the uppermost layer of the water column, a thin, life-giving skin across the open ocean. Depths of 4,000 meters or more lie below, wrapped in a darkness so complete that no photon of light from the sun has ever touched them since the ocean formed. The sunlit zone, by contrast, represents only about 2 to 3% of the ocean's total volume. Yet within this thin, sun-drenched shell, more life exists than in all the rest of the ocean combined. Every organism in the sunlit zone, from the tiniest phytoplankton to the mightiest blue whale, participates in a complex ecosystem shaped by light, temperature, and nutrient availability. The zone's productivity supports commercial fisheries that provide food for billions of people. Its photosynthetic activity generates oxygen for every land-dwelling creature. Its absorption of carbon dioxide buffers the planet from the full force of climate change. And yet, this vital zone is showing signs of stress, warming, acidifying, and losing species at an alarming rate. The daily vertical migration continues, resilient and unfaltering, a rhythm embedded in the very fabric of ocean life. But scientists wonder how long this rhythm can persist if the surface waters continue to change. If phytoplankton declines, the oxygen supply diminishes. If corals bleach, the reefs that shelter thousands of species crumble. If acidification weakens shells, the foundation of the food web erodes. The future of the sunlit zone is entangled with the future of humanity. For no creature on land can survive without the oxygen these waters produce, or the climate regulation they provide. As day turns to dusk and the vertical migrants begin their nightly ascent once more, the sunlit zone continues its ceaseless work. It feeds, breathes, and absorbs on a planetary scale, a silent engine driving the entire ocean system. But below its sun-warmed surface, a boundary approaches, a threshold where light finally gives out. Beneath 200 meters, photosynthesis becomes impossible. The brilliant greens and blues fade into an unending twilight, and a new world begins where creatures must find alternative ways to survive. The descent below this boundary will reveal the ocean's strangest inhabitants, adapted to a life where the sun never shines. The sunlit zone, for all its vibrancy, is only the beginning of the journey. However, the transition to darkness is not a sudden plunge, but a gradual dimming, and what waits in the fading glow will challenge every assumption about how life can exist. At exactly 200 meters below the surface, the ocean undergoes a transformation so profound that it might as well be the edge of another world. A pilot who once guided a submersible through these waters described a moment that would redefine his understanding of the deep. As the vessel rose toward the surface, he activated a strobe light to help the support ship locate them upon emergence. And every time the strobe flashed, everything around him flashed back. The darkness was not empty. It closed was not empty, was crowded with silent, glowing witnesses. In that instant, he realized he had been seeing only a fraction of the life surrounding him. He later described the revelation with a simple, unforgettable phrase. It was not a watery ocean. It was a living soup. That living soup begins precisely where the sun's reach fades to a faint, persistent blue glow. This is the twilight zone, formerly known to oceanographers as the mesopelagic zone, stretching from 200 to 1,000 meters deep. Here, the last remnants of sunlight diminish by a factor that defies comprehension. At the surface, light is blinding. At 200 meters, it is a dim, ghostly blue. At 500 meters, it is barely perceptible to even the most sensitive human eyes. And at 1,000 meters, the sun's rays vanish entirely, leaving behind a realm where the only illumination is manufactured by life itself. The twilight zone is not merely a transitional layer between the sunlit surface and the crushing abyss. It is a distinct and teeming ecosystem in its own right, one that encircles the entire globe as a continuous band of dark water. Stretching around the planet, this vast layer spans every ocean, every latitude, every climate zone. Its total volume is staggering, and within it swims an estimated 95% of all fish biomass on Earth. Some scientists calculate the weight of fish residing in this zone at approximately 10 billion tons, more fish weight than in all the other ocean zones combined. This is a fact that surprises many. The twilight zone, invisible to satellites and undetectable from the surface, has quietly supported the largest fish population on the planet, completely hidden from human awareness until relatively recently. Inhabitants of this dim realm have evolved in remarkable congruence with their environment. The lanternfish, among the most abundant vertebrates on Earth, owns a body covered with tiny light-producing organs arranged in species-specific patterns along its flanks. These thousands of microscopic photophores act like a constellation laid out on a living animal, allowing each lanternfish to identify its own kind in the gloom. There are over 250 species of lanternfish, each with a unique pattern of lights, each occupying a slightly different ecological niche within the twilight zone's layered depths. Even more numerous are the bristlemouths, small fish with jaws lined with fine hair-like teeth, giving them a microscopic gnashing appearance. The bristlemouth is possibly the most numerous vertebrate on the planet, with populations estimated in the hundreds of billions to trillions. These tiny animals, rarely exceeding 8 centimeters in length, patrol the twilight zone in uncounted numbers, feeding on zooplankton and serving as prey for larger predators. Their sheer abundance makes them an essential link in the twilight zone's food web, connecting microscopic life to the larger predators that stalk the top of this dark ecosystem. But the twilight zone boasts more than fish. The giant squid, the largest invertebrate on Earth, prowls these waters. This legendary animal, which can reach lengths variously reported and estimated at over 12 meters, remains one of the most elusive creatures on the planet. Despite centuries of nautical stories and modern exploratory efforts, the giant squid was not filmed alive in its natural habitat until the early 21st century. Japan's National Science Museum, along with Japanese broadcaster NHK and the Discovery Channel, captured the first live footage of live footage of Ensalagena, adult giant squid, in 2012, a feat accomplished after years of focused effort and the use of submersibles equipped with specialized low-light cameras. The animal displayed eyes the size of dinner plates, the largest eyes of any creature known to science, an adaptation that helps it gather every available photon in the twilight's dimness. Bioluminescence defines the twilight zone more than any other feature. Recent research indicates that more than 3/4 of the animals living in the mesopelagic produce their own light. This phenomenon, the production of light by living organisms, relies on enzyme-catalyzed chemical reactions. The results are spectacular beyond imagination. In the twilight zone, the darkness is stabbed with flashes of blue, green, and occasionally red light. The chemical machinery takes many forms. Some creatures harbor symbiotic bioluminescent bacteria. Others produce the luciferin and luciferase compounds internally. Still others have evolved complex light organs, complete with lenses and reflectors akin to tiny flashlights built into their bodies. The purposes of this glowing language are varied. For some, it serves as camouflage, a technique called counter-illumination, where creatures emit light matching the dim glow from the surface, effectively erasing their silhouettes from predators below. For others, bioluminescence aids communication. Lanternfish use their species-specific patterns to find mates in permanent darkness. And for still others, it is a hunting tool, luring prey within striking distance with an irresistible spark of light. Some species of dragonfish deploy a clever trick. They produce and detect red bioluminescence, a wavelength invisible to most other twilight zone inhabitants. This gives them a private communication channel and bits. A hunting advantage, their prey blinded to the very light that leads to their death. Every flash of light in this zone is a statement of life. Every glow, a call, a warning, or a final trap. The visual spectacle is so intense that an explorer experiencing it for the first time might feel less like a scientist and more like a traveler to an alien planet, where the geography is not made of rock and water, but of photons and silence. The twilight zone is one of the most visually spectacular regions of the ocean, a living light show hidden beneath the waves. Yet for all its wonders, the twilight zone is physically punishing. The pressure here ranges from 20 to 100 times surface atmospheric pressure, a crushing force that would kill an unprotected human instantly. Divers cannot survive here without heavy machinery. Even with advanced submersibles, exploration is costly and challenging. This inaccessibility explains why the twilight zone remains so poorly understood. But above all, the twilight zone's inhabitants have found a way around a fundamental problem: the eternal scarcity of food. There are no plants here. Photosynthesis is impossible. So how do these billions of fish survive? The answer lies in another remarkable pattern of behavior, a daily pilgrimage of scale, so enormous it can only be described as synchronized gymnastics performed by the entire planet's ocean life. Every single night, this darkness empties out. The sequel to this journey, the largest animal migration on Earth, will carry these creatures upward to feed under the cover of darkness, then drive them back down below the defense line of light. That story begins at the very moment the sun sets over the world's oceans. Every evening, As dusk settles across the world's oceans, the largest migration on Earth begins. From the dim waters of the twilight zone, billions upon billions of organisms, fish, squid, crustaceans, and gelatinous creatures, beyond counting, rise toward the surface. They travel hundreds of meters, sometimes more than 400, in a coordinated ascent driven by a single primal impulse: hunger. Under the protective cloak of night, they feed on the phytoplankton and zooplankton that thrive in the sunlit surface waters. Then, before the first rays of dawn touch the horizon, they reverse course, descending back into the safety of darkness. This daily round trip, repeated without fail across every ocean on the planet, moves an estimated 10 billion tons of fish alone, not to mention the countless invertebrates that join the procession. It is the greatest movement of animal biomass on Earth, and yet it remained entirely unknown to humanity until the 20th century. The mechanics of this migration reveal a sophisticated interplay between light, predation, and survival. As daylight fades at the surface, the twilight zone's inhabitants use the diminishing light as their cue. They ascend, tracking a narrow band of illumination called the abyssal of dawn, a depth where light intensity remains constant enough for their sensitive eyes to function. Most twilight zone species possess eyes specially adapted for low light vision, with large pupils and enhanced rod cells that maximize photon capture. These eyes allow them to see in conditions that would be total darkness to a human, yet they are still vulnerable to predators that hunt by sight. The strategy is simple: feed under the dim cover of night when surface predators are less effective, then retreat to darkness before full daylight exposes them to danger. This rhythm is so deeply ingrained that it shapes the entire ecology of the twilight zone. Predators follow their prey upward, and larger predators follow them, creating a vertical food chain in constant motion. Sperm whales, which dive to depths of over 1,000 meters to hunt giant squid, time their descents to coincide with the migration. Tuna, billfish, and other commercially valuable species also exploit this nightly bounty, chasing the ascending swarms toward the surface. The twilight zone's residents have become the engine that fuels much of the ocean's open water productivity, transferring energy from the sunlit surface down into the depths. But living in this zone presents challenges that go far beyond the mere absence of light. The pressure at 200 meters is roughly 20 times atmospheric pressure at sea level. At the zone's lower boundary of 1,000 meters, that pressure reaches 100 times surface levels, a force of approximately 1,000 tons per square meter. No unprotected human diver could survive even a fraction of this journey. The deepest free dive without equipment barely reaches 100 meters. And even with scuba gear and specialized gas mixtures, and divers face life-threatening conditions below 150 meters. The twilight zone lies beyond the reach of human bodies entirely, accessible only through the thick hulls of submersibles or the remote eyes of deep-sea robots. Creatures of the twilight zone have adapted to this crushing environment in remarkable ways. Many species lack the rigid, bony skeletons found in surface fish, replacing them with soft, gelatinous bodies composed mostly of water. This reduces their density, making it easier to maintain buoyancy under immense pressure, and also allows them to compress slightly without damage. Their swim-thinat bladders, organs that help surface fish control buoyancy, are either absent or greatly reduced because the gas they contain would become dangerously compressed or even collapse the organ itself. Instead, many twilight zone fish rely on high levels of fats and oils within their tissues, which provide natural buoyancy and are less compressible than gases. The cold adds another layer of difficulty. Temperatures in the twilight zone hover near 4 degrees Celsius, barely above freezing, with little seasonal variation. This low temperature slows metabolic processes, reducing the energy demands of these creatures and allowing them to survive on the sparse food resources that drift down from above. Larger body sizes, slower swimming speeds, and efficient energy storage all characterize Twilight Zone residents. Adaptations that have evolved over millions of years to cope with an environment where energy is scarce and food arrives unpredictably. Perhaps the most striking adaptation, however, is the phenomenon of various bioluminescent strategies already explored. The ability to produce light has become so essential that an estimated 3/4 of Twilight Zone animals use it in some form. It serves as a tool for finding mates in darkness, as a distraction to confuse predators, and even as a form of communication between rivals. Some species release glowing clouds into the water when threatened, creating a temporary smoke screen that disorients attackers while the animal escapes. Others use their lights to blind prey, momentarily stunning them long enough to be captured. This constant flickering conversation of light is the Twilight Zone's primary language, spoken in a dialect of flashes, pulses, and sustained glows that scientists are only beginning to decipher. Despite the scientists are only beginning to decipher harsh conditions, the Twilight Zone supports an astonishing diversity of life. Recent studies suggest the biomass of fish in this layer may be 10 times greater than previously estimated, a revelation that has transformed scientific understanding of ocean ecology. This discovery has also sparked commercial interest. Fisheries operators, having depleted many surface populations, are beginning to look toward the Twilight Zone as a potential new food source. The animals here, particularly lanternfish and bristlemouths, are rich in oils and proteins, and estimates of their abundance have made them attractive targets for industrial-scale harvesting. Yet scientists caution that removing these creatures could have catastrophic consequences since they play a central role in the carbon cycle, transporting vast amounts of organic matter from the surface to the deep ocean each night. The carbon transport occurs through a process called the biological pump. When Twilight Zone creatures rise to feed, they consume carbon-rich organisms at the surface. When they descend and excrete waste, or when they die and sink, that carbon is carried down into the depths, where it can remain sequestered for centuries. This daily migration effectively pulls carbon dioxide out of the atmosphere, helping regulate global climate. Disrupting this system through overfishing, for example, could release stored carbon and accelerate climate change in ways that are difficult to predict. Beyond the practical concerns, the twilight zone remains a frontier of discovery. Explorers using remotely operated vehicles have captured footage of transparent creatures with bodies like glass, of siphonophores stretching longer than a blue whale, of fish with tubular eyes that look upward through their transparent skulls. Each dive reveals new species, new behaviors, and new questions. Scientists estimate that only a tiny fraction of Twilight Zone species have been formally described. Countless others await discovery. Below the Twilight Zone's lower boundary at 1,000 meters, however, a different world begins. There, sunlight vanishes entirely, never to reappear. The pressure doubles and doubles again. Temperatures drop further, and food becomes rarer still. Yet even in this perpetual night, life persists. Creatures like the gulper eel, the anglerfish, and the vampire squid have evolved strategies so extraordinary they seem almost supernatural. What happens to life when light disappears completely? That question, and the strange answers awaiting in the midnight zone, builds the descent deeper into the abyss. At 1,000 meters below the ocean's surface, sunlight dies completely. Not fades, not dims, but vanishes into an absolute, unbroken blackness that has never known a single photon of solar illumination. This is the bathypelagic zone, the midnight zone, a realm that stretches from 1,000 meters down to 4,000, encompassing a volume of water so vast it would swallow every continent on Earth with room to spare. A human dropped into these waters without protection would be crushed within milliseconds by pressures exceeding 100 times surface atmospheric levels, the equivalent of having dozens of elephants stacked on every square centimeter of flesh. And yet life thrives here. The creatures that call this darkness home are so alien in form and function that they appear to have evolved on another planet entirely. Among them swim gulper eels with mouths that unhinge like living traps, vampire squid draped in webbed cloaks, and the iconic anglerfish, dangling a map, glowing beacon from its forehead as it hunts in the eternal night. How do these animals survive where food is scarcer than anywhere else on Earth, where every meal might be the last, and where encountering another creature could mean becoming its dinner? The answers reveal a world of brutal efficiency, evolutionary genius, and desperate patience. The midnight zone is defined by absence. No sunlight penetrates these depths, so no photosynthesis can occur. Not a single plant or algae can grow here. The water temperature hovers near 4 degrees Celsius, just above freezing, with virtually no seasonal variation. The pressure at the zone's upper boundary is around 100 times surface pressure, and at its lower reaches, it quadruples further, reaching forces that would crumple steel submarines like tinfoil. Food, the fundamental currency of all life, arrives in a slow, unpredictable trickle from above, in the form of marine snow, a constant drizzle of dead organisms, fecal matter, shed body parts, and other organic debris that falls from the sunlit and twilight zones above. By the time this material reaches the midnight zone, most of its nutritional value has already been stripped away by the billions of hungry mouths it passed on its journey downward. What remains is a ghost of sustenance, barely enough to support the scattered inhabitants of this lightless world. In this landscape of extreme scarcity, survival demands efficiency. Above all else, the gulper eel, known scientifically as Europharynx pelicanoides, has evolved one of the most extreme feeding strategies in the animal kingdom. Its mouth, which opens wider than its entire body, is lined with hundreds of tiny, sharp teeth. Unlike the stiff jaws of most fish, the gulper eel's jaws are loosely connected, allowing stick-eater them to expand dramatically, forming a massive pouch capable of swallowing prey larger than the eel itself. This is not a hunting tactic for frequent meals. Rather, it is a survival strategy for the rare moments when substantial prey appears. When a fish or squid stumbles into range, the gulper eel strikes with explosive force, engulfing it whole and storing the meal in its expandable stomach. Days, weeks, or even months may pass between such feeding opportunities. The eel's slow metabolism allows it to survive on a single large meal for extraordinarily long periods, a necessity in a world where meals arrive unpredictably, if at all. The anglerfish has developed an even more famous solution to the midnight zone's challenges. Its dorsal spine extends forward over its mouth, ending in a bulbous, fleshy lure containing bioluminescent bacteria. This living flashlight, glowing with a cold blue-green light in the darkness, serves as a beacon to attract prey. In the pitch-black waters of the midnight zone, any glimmer of light is a powerful attraction. Smaller fish and crustaceans, drawn by curiosity or hunger, swim toward the glow and unknowingly toward the anglerfish's cavernous mouth, lined with long needle-like teeth, angled inward to prevent escape. The anglerfish's strategy is one of patient ambush. It remains motionless, conserving energy, until its lure successfully entices prey close enough to strike. This adaptation is so effective that many anglerfish species cannot survive without it. The lure is their primary hunting tool, and its loss would mean starvation. The glowing bulb, it turns out, is not just a trap for prey. It is a life or death necessity in a realm where every calorie must be earned through extreme cunning. The vampire squid, despite its terrifying name, is a study in passive survival. It is not actually a squid, but a cousin of octopuses and cuttlefish, and it does not hunt living prey. It is a detritivore. Its diet consists almost entirely of marine snow, the falling organic debris that sustains the entire midnight zone. The vampire squid catches this detritus using two specialized filaments known as filaments of ash, which extend many times its body length and are lined with microscopic hairs to capture drifting particles. It also employs a unique defense mechanism. When threatened, it wraps itself in its own webbed arms, creating a cloak that makes it appear much larger than it actually is. Bioluminescent spots on its skin flash rapidly in a disorienting display, giving it time to retreat into the darkness from which it emerged. Its body is covered with light-sensitive cells that keep it perpetually aware of its surroundings, even in absolute darkness. This passive lifestyle, consuming whatever drifts down from above without expending energy to chase prey, is perfectly adapted to a world where energy must be conserved at all costs. The pressure of the midnight zone presents a challenge that affects every aspect of life here. At 1,000 meters, water exerts a force of approximately 100 atmospheres, equivalent to roughly 1,000 tons per square meter. At 4,000 meters, that pressure quadruples. Creatures of the midnight zone have evolved to cope with this crushing weight in several ways. Many species have soft, gelatinous bodies that are nearly the same density as water, allowing them to float without expending energy on swimming. This waterlogged tissue compresses slightly under pressure without damage, unlike the rigid skeletons of surface fish that would crack and shatter. The giant isopods, related to the common woodlouse, have non-compressible shells and move slowly to minimize energy expenditure. The anglerfish and gulper eel possess highly reduced skeletal structures, their bones and muscles adapted to function under extreme compression. This is why so many midnight zone animals appear almost ghostly in photographs. Translucent, soft-bodied, with translucent or transparent exterior surfaces that offer minimal resistance to the crushing dark water. Vision in the midnight zone takes on a strange and limited role. The eyes of many resident fish are larger relative to body size than those of their surface counterparts, and they are often directed upward to catch the silhouettes of prey against faint bioluminescent glow from above. Some species, having lived for generations in complete darkness, have secondarily lost their eyes entirely, remaining astounded. The eyes of the midnight zone are actually less useful as the depth increases. At 1,000 meters, there is simply no light to see by. Instead, these creatures rely increasingly on other senses, on detecting the subtle water disturbances made by nearby animals through a lateral line system, on chemosensory receptors that can trace chemical trails in the water, and on an array of bioluminescent communication systems. The lights of the midnight zone are not used for camouflage as they are at twilight. They are used for signaling and hunting, each flashing pattern carrying a message of territorial claim, mating availability, or predatory intent. Food scarcity in the midnight zone is absolute. Estimates of biomass suggest that the population density here is only a fraction of that found in the twilight zone above, and a tiny proportion of the sunlit zone at the surface. But these estimates are incomplete. Scientists have only begun to appreciate how life persists so deep below, and recent discoveries have revealed new feeding strategies that defy previous understanding. Some fish, like the stoplight loosejaw, have evolved photophores that emit red light, a wavelength invisible to most other deep-sea organisms, allowing them to hunt without being detected by standard vision. Others have developed highly sensitive hearing, enabling them to detect potential prey by their sounds in the water column. The midnight zone intelligence's deep resourcefulness demonstrates that even in the most extreme selective conditions, life will find a way. Beneath these adaptations lies an even more astonishing truth. The most significant predators of the midnight zone are not large fish, but rather the gelatinous drifting hunters that move through the water column. The ctenophores, hydromedusae, and siphonophores that expand their apparently fragile bodies in loops across the darkness. Among them, the anglerfish is a rare vertebrate in this alien habitat, one that must compete with beings whose bodies are almost entirely water and whose hunting strategies are slow, ambush-based, and brutally efficient. The pelagic communities of the Midnight Zone are organized not by the sunny hierarchies of shallow waters, but by the logic of absolute shortage, where food falls and life waits silently, motionlessly, with patience born of necessity. A deep-sea biologist once described the Midnight Zone as painting a picture of the future of ocean study. The surface is where we search for answers, he said, but the Midnight Zone is where we find them. The adaptations of gulper eels, anglerfish, and vampire squid reveal that resource scarcity does not preclude innovation. It may drive it to new extremes. Yet, even these magnificent adaptations cannot fully explain how this entire zone survives. Some point to the hydrothermal vents that punctuate the Midnight Zone at various points, releasing chemically rich water that supports entire ecosystems independent of the sun. Others point to the bizarre reproductive desperation of species like the anglerfish, whose males fuse permanently to females, sharing their bloodstream forever. The answer to the Midnight Zone survival lies in these reproductive strategies, suits of evolutionary self-sacrifice and fusion, so strange that recovery from the very mention defies easy storytelling. The extremes of the Midnight Zone will only intensify as the descent continues. Among the anglerfish population of the Midnight Zone, one of the most shocking mating strategies in all of nature unfolds in absolute darkness. When a young male anglerfish hatches from his egg, he enters a world of terrifying emptiness. He is tiny, barely a few centimeters long, with poorly developed fins and a digestive system that begins to atrophy within days. He is not adapted for hunting. He barely eats. Instead, he swims through the vast blackness, guided by an exquisite sense of smell, following chemical trails that could lead him to a female or to death by starvation. This quest is a desperate race against time, a 500-meter journey into obscurity with no guarantee of success. And if he does not find a mate quickly, the young male anglerfish simply dies. For the species that reach this desperate goal, the reward is both salvation and a kind of biological imprisonment. When the male finds a female often many times larger than himself, he latches onto her with his sharp teeth. His body slowly fuses to her flesh, his skin merging with hers until the boundary between two individuals becomes indistinguishable. His bloodstream connects to hers, his organs, save for his testes, gradually degenerate and disappear. His eyes waste away, his fins dissolve, and his digestive tract vanishes entirely, for he no longer needs them. He becomes essentially a permanent parasitic appendage, a living sperm bank attached to the female's side, nourished by her blood, fertilizing her eggs whenever she spawns. Some females carry several such males fused to their bodies, having accumulated mates during their years of wandering the depths. This phenomenon, unique among vertebrates, ensures that when a female is ready to spawn, a mate will always be available, critical in a world so sparse that encountering another anglerfish by chance might happen only once in a lifetime. This reproductive strategy is one of the most bizarre examples of evolutionary adaptation ever discovered, a radical solution to the midnight zone's fundamental problem. Life here is so thinly dispersed and food so scarce that encounters between adults of the same species are vanishingly rare. A fish that must search for a mate every breeding season would likely starve before reproduction occurred. By fusing permanently, mated pairs guarantee reproductive success. The female carries her male partners with her, always ready, never lost, never requiring a second search. The cost of this strategy, the complete absorption of the male's individuality and even his consciousness, is a sacrifice so extreme that scientists initially refused to believe it when first described in the early 20th century. The rarity of food that drives such desperate solutions also dictates every other aspect of midnight zone life. Marine snow, the constant drizzle of organic particles that chance falls from above, is the primary source of nutrition for the entire zone. Every dead phytoplankton cell, every discarded shell, every fecal pellet from a twilight zone creature sinks slowly through thousands of meters of water before reaching this depth. The journey takes weeks or even months, during which bacteria and other decomposers consume a substantial fraction of the material's nutritional value. What finally arrives is often little more than mineral residue, a few precious calories scattered across countless cubic kilometers of water. Studies using sediment traps, devices that collect falling particles, have measured marine snow fluxes in the midnight zone at roughly 1 to 3% of the organic carbon production occurring at the surface. This is the food that sustains an entire alien ecosystem. To harvest this meager rainfall, the creatures of the midnight zone have evolved into masterful filterers and patient scavengers. Many species are essentially living nets, spreading specialized appendages or expanding gelatinous bodies to capture whatever drifts within reaching distance. The vampire squid, with its extended filaments, is one such example. Others, like the deep-sea medusa jellyfish, use the water currents to push particles into their outstretched tentacles. But marine snow does not provide enough energy for active hunting of large prey, which explains the prevalence of passive ambush strategies, like the anglerfish with its bioluminescent lure, or the gulper eel, waiting in complete stillness until a meal swims within striking range. Every adaptation in the midnight zone orbits the central unyielding constraint. Energy must be hoarded, each meal squeezed for its maximum worth, each movement metabolically budgeted as if it were coin. The physiological innovations required for such survival are staggering. Many midnight zone fish have evolved extremely low metabolic rates, drastically reducing their food requirements. Some species slow their bodily functions to such a degree that they might survive a year or more between meals. Others possess stomachs so expandable that a single successful hunt for a large prey can sustain them for months. The pressure which would crush a submarine, per se, pressure which would crush a submarine, has been accommodated over evolutionary time by the loss of compressible gas-filled spaces, the dissolution of rigid skeletal structures into flexible cartilage, and the replacement of large swim bladders with lipid deposits. Even their protein structures have adapted to function properly under extreme compression, resisting the denaturation that would disable surface-dwelling organisms at these depths. Scientists study this hidden world primarily through remotely operated vehicles, or ROVs. These robotic submarines, controlled via fiber optic cables from surface vessels, carry cameras, lights, and sampling arms down to depths where humans cannot safely travel. Since their development in the late 20th century, ROVs have revolutionized deep-sea exploration. They have filmed anglerfish luring in the dark, vampire squid drifting through the black, and never-before-seen species engaging in previously unknown behaviors. Operating an ROV in the midnight zone is a painstaking process. Operators guide the vehicle excruciatingly slowly to avoid disturbing the water column, using only the glow of the vehicle's lights to pierce the darkness. Many encounters last only seconds before the shy creatures retreat into obscurity, offering tantalizing glimpses and frustratingly partial data. One of the fundamental assumptions of midwater research is that ROVs provide a completely unperturbed view of life in the deep. This assumption, according to veteran deep-sea researchers, is likely false. Studies have shown that the lights and sounds of remotely operated vehicles attract curious creatures, including some of the deep's most elusive predators. The very presence of an observation platform may be altering the behavior of the animals being observed. This caveat underscores the difficulty of understanding a world so alien that our simplest sensory inputs, light, sound, gravity, take on entirely different meanings. For every midnight zone creature observed, perhaps 100 more flee before the lights, their existence revealed only by the blip of sonar, the flash of bioluminescence detected by specialized sensors, or the anomalous specimens brought to the surface in fragile nets. These exploratory voyages have yielded a sobering realization about the lower limits of the midnight zone. Descending past 4,000 meters, the crushing darkness gives way to a new realm, the abyssal plains. This vast, nearly featureless expanse of silt and sediment covers more of Earth's surface than all land combined, a great desert of the deep. But submerged within and descending beyond lie features that resemble science fiction. Ocean trenches have been located on Earth's crust, wounds gouged deep enough to produce temperatures and pressures beyond comprehension. What survives in those ultimate abyssal redoubts remains one of the final frontiers of astronomy. leaving open the question of what monstrous unseen survivor might be flickering its lights in the last depths of the Hadal Zone. At 4,000 meters below the surface, the craggy slopes of the continental margins finally give way to something almost unnerving in its uniformity. The seafloor flattens into an expanse so level and so vast that it rivals the Great Plains of North America in sheer horizontal monotony, except this desert lies beneath nearly 4 kilometers of crushing, near freezing water. These are the abyssal plains, the most extensive geographic feature on the planet, covering more than 50% of Earth's entire surface. No mountains punctuate this horizon, no valleys interrupt its gentle slope. The abyssal plain is a world of stillness, of slow time, where a single grain of sediment might take centuries to settle, and where life persists under a pressure of approximately 6 tons per square inch, enough to instantly annihilate any surface-dwelling creature. The smoothness of these plains is not accidental. It is the product of patience operating on a geological timescale. For tens of millions of years, a steady rain of fine particles has drifted down from the waters above, dust blown from continents, the microscopic shells of dead plankton, the pulverized remains of countless organisms that lived and died in the sunlit zones far overhead. This constant gentle precipitation, known as pelagic sediment, settles grain by grain, forging layer upon layer over staggering spans of time. The total sediment deposition rate in remote areas is estimated at a mere 2 to 3 centimeters per 1,000 years. At this pace, a single meter of abyssal mud requires roughly 30 to 50,000 years to accumulate. The result is a blanketing that gradually smooths over the rugged volcanic terrain of the oceanic crust beneath, erasing ancient ridges and filling ancient valleys until the seafloor becomes astonishingly level. This process has been running for so long that the abyssal plains hold within their layered sediments a stiments, complete archive of Earth's climatic history. Each stratum contains the fossilized remains of microorganisms whose oxygen isotope ratios reveal ancient ocean temperatures. Buried layers of ash record volcanic eruptions from epochs when dinosaurs still walked the surface. Microscopic pollen grains blown from ancient forests, preserved in the deep, cold mud, trace the shifting of continents. The abyssal plain is not merely a featureless desert, it is the planet's most complete diary, written in silt. Yet despite the crushing pressure and the absolute darkness, the abyssal plains teem with life, not in the abundance of the sunlit shallows, but in a sparse, hardy population scattered across the endless sediment. The most common residents are sea cucumbers, which slowly crawl across the muddy bottom in search of the organic detritus that falls as marine snow. These slug-like creatures, some reaching lengths of over a meter in the deep sea, use tube feet to inch forward, ingesting mouthfuls of sediment and extracting whatever scant nutrition they can find. Some deep-sea sea cucumbers have evolved to become essentially living conveyor belts, processing vast quantities of mud. A single individual may pass tons of sediment through its body over its lifetime, contributing to the slow churn of the abyssal surface. Alongside the sea, cucumbers move brittle stars, close relatives of starfish with long, slender arms that allow them to glide over the soft sediment without sinking. These delicate creatures, sometimes gathered in dense aggregations reminiscent of underwater forests, stripped of their trees, feed on any organic particles that settle within reach. Their arms, covered in cilia and mucus, sweep food toward their central mouth cavities, with a motion so slow and regular that observing them in real time reveals almost no perceptible movement. Time on the abyssal plane moves at a different pace, and the brittle stars have mastered it. Perhaps the most remarkable residents are the giant isopods, crustaceans related to the common woodlouse, but reaching lengths that can approach 40 centimeters. These armored scavengers, with their segmented shells and 17 pairs of legs, patrol the abyssal floor in search of any food that might fall from above. Their oversized antennae detect chemical traces in the water, guiding them toward the fading remains of a whale fall or the scattered debris of a dead fish. Giant isopods are remarkably patient hunters. Some have been observed in laboratory settings, surviving for over 4 years without food. Their metabolism slowed to near dormancy. They are the vultures of the abyssal plain, recycling the final organic remains of the ocean's uppermost layers. This vast region, with its sparse and scattered inhabitants, was once believed to be a biological desert, a vision promoted by early 20th century oceanographers who imagined the deep sea as a lifeless, hostile void. The revelation of abyssal life did not come easily. The first photographs of sea cucumbers plowing through abyssal mud were captured only in the 1960s, shocking a scientific community that had long accepted the absence of life at such depths. Subsequent exploration revealed not only abundance but diversity. The abyssal plains, it turns out, support more species than scientists ever predicted. A single square meter of abyssal mud may contain dozens of species of small invertebrates, worms, and crustaceans, whose total biomass, though thinly dispersed, represents a substantial share of Earth's animal life. But the abyssal plain's most transformative secret was not its crawling inhabitants. It was the discovery that punctuated, in the most dramatic way imaginable, human understanding of where life can exist. Beneath the sediment, along the mid-ocean ridges that snake through every ocean basin, hydrothermal vents erupt from the seafloor, spewing superheated, mineral-rich water into the frozen darkness. These volcanic chimneys, some towering tens of meters high, pour forth water heated to temperatures exceeding 300 degrees Celsius. Water that would instantly boil at the surface, but remains liquid here because of the immense pressure. Around these vents, a completely unexpected ecosystem flourishes, one that draws its energy not from sunlight, but from the chemical compounds dissolved in the vent fluids, a process called chemosynthesis. This second, hidden tree of life, growing entirely without a single photon of solar energy, remains the most astonishing chapter of abyssal discovery. Its full story, one that rewrote the boundaries of life itself, waits just beyond this gentle drift across the vast, cold desert of the deep. In February 1977, a team of geologists aboard the research vessel NOR watched their deep-sea camera send back images that would shatter a century of biological certainty. They had descended to the Galapagos Rift, approximately 2,500 meters below the surface, expecting to find the barren, lifeless abyss that textbooks described. Instead, their floodlights illuminated something impossible. Clusters of giant tube worms, their crimson plumes waving in the superheated water, alongside fields of pale clams and crowds of albino crabs. No sunlight reached this depth. No plant could grow here. Yet life flourished in densities that rivaled the richest coral reefs. The discovery forced a complete rewrite of biology's most fundamental assumption that all life on Earth ultimately depended on the sun's energy, and revealed a second, hidden tree of life sustained entirely by chemical energy from the planet's interior. The source of this astonishing abundance lay in the jagged basalt chimneys rising from the seafloor like cathedral spires from another world. These were hydrothermal vents, formed where seawater seeped through cracks in the oceanic crust and met magma-heated rock below. The water superheated to temperatures exceeding 300 degrees Celsius, dissolved minerals and gases from the surrounding stone before being violently ejected back into the freezing abyss. The meeting of scalding, mineral-laden water with mere freezing seawater caused dissolved compounds to precipitate, building towering structures of sulfide and sulfate that could reach heights of over 40 meters. Some of these chimneys, known as black smokers, belched plumes of dark, particle-rich water that rose like smoke from an underwater chimney. Others, the white smokers, emitted cooler, paler fluids. Every vent was a volcano in miniature, a window into the Earth's molten interior. Around these fiery oases, life had assembled in astonishing abundance. The giant tube worms, scientifically known as Riftia pachyptila, grew to over 2 meters in length, their bright red plumes extending from white, straw-like tubes anchored to the rock. They possessed no mouth, no stomach, no digestive tract at all, surviving entirely through a symbiotic relationship with bacteria living inside their bodies. These chemosynthetic bacteria oxidized hydrogen sulfide from the vent fluids, converting the chemical energy into organic compounds that nourished their hosts. The tube worms' plumes absorbed the sulfide from the water and transferred it directly to their internal bacterial partners. In exchange, the bacteria supplied the worms with all the sugars and proteins they needed to grow to lengths that boggled the imagination of scientists who first measured them. The vent fields also hosted dense communities of giant clams, some reaching lengths of over 30 centimeters. Their shells covered with the same symbiotic bacteria that powered the tube worms. These clams, belonging to the genus Calyptogena, lacked the digestive systems of their shallow water relatives, depending entirely on their internal bacterial gardens. Swarms of blind white shrimp, belonging to species found nowhere else on Earth, crowded the vent chimneys, grazing on bacterial mats that coated every available surface. Pompeii worms, covered in fine hair-like bristles and bearing bacterial colonies on their backs, clung to the chimney walls, enduring temperature extremes that would kill any other known metazoan. The vent ecosystem, far from being a sparse abyssal outpost, was more densely populated than most surface environments, a teeming city of life clustered around the deep Earth's chimneys. This discovery, later recognized with the naming of over 500 new species found nowhere else on the planet, proved that life could indeed thrive without photosynthesis. The revelations did not stop with mere survival. They suggested that life on Earth may have originated in such environments. The last universal common ancestor, the hypothetical organism from which all living things descended, may well have been a thermophilic microbe living near a hydrothermal vent billions of years ago. The vents, which some astrobiologists now study as analogs for potential ecosystems on Jupiter's moon, Europa, have become central not only to understanding Earth's biology, but also to the search for life elsewhere in the universe. If life can exist on chemical energy alone, in total darkness and crushing pressure, perhaps it can exist anywhere. Liquid water meets rock, even beneath the ice of distant moons. The shock of 1977 was amplified by a second realization. The abyssal plains were not static deserts, but dynamic realms shaped by slow-moving currents that connected the entire ocean in a single circulatory system. The deep water of the abyssal plains is part of a planetary conveyor belt, a thermohaline circulation driven by differences in temperature and salinity. At the polar regions, surface water cooled and became denser, sinking to the abyssal depths and spreading across the ocean floor. This deep water crept along the abyssal plains at speeds measuring mere centimeters per second, yet over decades and centuries, it transported oxygen, nutrients, and heat across thousands of kilometers. The entire world ocean, from sunlit surface to Hadal Trench, is connected in one vast, slow-moving system where a molecule of water might complete a full circuit over 1,000 years. These abyssal currents play a critical role in regulating Earth's climate. They sequester carbon dioxide from the atmosphere, transporting it to the deep ocean where it remains for centuries. They distribute oxygen to the deepest seafloors, sustaining the sparse but persistent life of the abyssal plains. They also transport the larvae of deep-sea creatures far beyond their point of origin, mixing and mingling populations across ocean basins. The abyssal plains are not islands of isolation, but junctions in a globally interconnected system. A change in surface temperature near Greenland, scientists now had been scientists, now warn, could slow this deep circulation with consequences for the entire planet. There is also a darker current flowing through these depths. Microplastics, persistent chemical pollutants, and even the residue of nuclear weapons tests from the 1950s and 1960s have been found in abyssal sediments. The same slow currents that distribute oxygen also distribute industrial contamination, penetrating every layer of the ocean, including the most remote regions on Earth. The discovery of plastic debris in the stomachs of amphipods collected from the Mariana Trench nearly 11 kilometers deep, served as a stark reminder that human reach extends to the very floor of the world's deepest wounds. As the descent continues beyond the abyssal plains, past 4,000 meters, the seafloor changes once more. The flat expanses give way to the steep walls of oceanic trenches, where tectonic plates collide and one crust plunges beneath another. Here in the Hadal Zone, depth increases without limit, and pressure becomes something that defies even the imagination of the abyssal survivors. The remaining swaths of the Pacific floor still hold secrets, their vast, unexplored recesses still untouched by human probes. What lies in the deepest trenches, those vertical wounds that plunge toward the planet's mantle, is the final frontier of the descent. The track from the final frontier, the pathways down to the very abyssal heart of the planet, is well worn in human imagination yet almost entirely unexplored. That abyss, descending to depths below 6,000 meters, holds life that has never seen a surface or felt the touch of sunlight, and even fewer human witnesses have beheld anything in these final cosmic obscurities. The descent continues. The deepest point on Earth would swallow Mount Everest, whole and still leave its summit more than a kilometer beneath the waves. Yet this measurement, astonishing as it is, barely hints at the strangeness of what lies at the bottom of the ocean's trenches. These are not gentle slopes or gradual descents, but vertical wounds in the planet's crust, V-shaped chasms carved by the slow collision of tectonic plates over millions of years. And within these lightless, crushing abysses, where pressure reaches 8 tons per square inch and temperatures hover just above freezing, scientists have discovered a fish that looks like a pink, translucent ghost. A creature whose gelatinous body has evolved to thrive in conditions that would instantly destroy any other vertebrate on Earth. This is the Hadal Zone, a realm known to oceanographers as the Hadopelagic, named for Hades, the ancient Greek god of the underworld. It begins at approximately 6,000 meters below sea level and extends downward to the deepest trench floors, plunging past 11,000 meters at its ultimate extreme. The zone occupies a mere 1% of the world's seafloor surface, yet within that sliver of territory, life has pushed the boundaries of biological possibility further than anywhere else on the planet. The geography of the Hadal Zone is unique among ocean layers. Unlike the sunlit, twilight, midnight, and abyssal zones, which exist as horizontal bands encircling the globe, the Hadal Zone exists only in isolated, fragmented pockets. There are approximately 37 deep-sea trenches on Earth, and roughly 94% of the Hadal Zone is found within these subduction trenches, where one tectonic plate is forced beneath another in a slow, grinding collision that has been ongoing for tens of millions of years. The Pacific Ocean hosts the vast majority of these trenches, ringed by the volatile Pacific Ring of Fire, where earthquakes and volcanic eruptions testify to the immense forces at work beneath the sea floor. The Mariana Trench, the most famous of these chasms, stretches over 2,500 kilometers across the western Pacific, arching south of Japan toward the island of Guam. At its deepest point, a feature known as Challenger Deep, located at its southern end, the trench floor lies approximately 11,000 meters below the surface. A depth that remains, by any reasonable measure, the closest point on Earth's surface to its molten interior. The trench was formed where the enormous Pacific Plate, moving steadily westward, dives beneath the smaller Mariana Plate, dragging ancient seafloor down into the mantle. The plate boundary is a zone of constant, grinding violence, though the movement occurs so slowly, mere centimeters per year, that its effects are apparent only over geological time. Life in the Hadal zone faces challenges that would annihilate any surface-dwelling organism within moments. The hydrostatic pressure at 6,000 meters exceeds 600 times atmospheric pressure at sea level, and at the bottom of the Mariana Trench, it reaches over 1,000 times. A human unprotected by a submarine would be crushed instantly, the air in their lungs compressed to liquid, their bones shattered, their flesh reduced to a thin slurry. Even the most robust deep-sea submersibles, engineered with thick titanium hulls, groan and creak under the strain. Yet within this crushing darkness, the Hadal Zone hosts a surprising diversity of life. Amphipods swarming in vast numbers, sea cucumbers crawling across the sediment, and at the very limits of vertebrate survival, the snailfish, the Hadal snailfish, discovered relatively recently in the Mariana Trench at depths exceeding 8,000 meters, is perhaps the deepest living vertebrate ever recorded. Specimens observed by scientists range from translucent pink to pale white, with bodies so gelatinous they appear almost liquid in their pressure-resistant form. The snailfish lacks a swim bladder, the gas-filled organ that provides buoyancy in shallower fish, because such a structure would be crushed instantly at Hadal depths. Instead, its body is composed largely of water and jelly-like tissue, nearly the same density as the surrounding seawater. This allows it to hover effortlessly above the trench floor without expending energy on active swimming. Its skeleton and skull are markedly reduced in weight, composed of soft, flexible cartilage rather than heavy bone. Its eyes are small, adapted to detect the faint bioluminescent flashes of prey rather than detailed images in a world where sunlight has never penetrated. The snailfish's physiology offers a remarkable solution to the problem of pressure. Studies have revealed that its cells contain high concentrations of a compound known as trimethylamine N-oxide, or TMAO, which protects proteins from being crushed and denatured under extreme compression. This osmolyte, found in increasing concentrations in fish living at greater depths, essentially fills the cellular space with a molecule that resists compression, safeguarding the structural integrity of enzymes and receptors. In shallower fish, TMAO concentrations are relatively low. In the Hadal snailfish, they are so elevated that scientists believe the fish may be operating at the very physical limits of vertebrate life, beyond depths of roughly 8,400 meters. Even this biochemical protection may not be sufficient, which may explain the absence of any fish deeper than this horizon, a threshold known informally among researchers as the snailfish's wall. Closer to the trench floor, below the reach of any fish, other creatures dominate. Amphipods, small, shrimp-like crustaceans, thrive in staggering abundance. Some species grow to startling sizes, their bodies reaching lengths of over 20 centimeters. Adaptations to the immense pressure that slows their metabolism and extends their lifespans. These amphipods scavenge for any organic debris that falls from above, feeding on the meager rain of marine snow that reaches such depths, as well as on the carcasses of dead fish and whales that occasionally drift down from the sunlit world. The trenches act as natural funnels, channeling sediment and organic matter from the surrounding slopes into their deepest recesses. As a result, levels of organic material on trench floors may actually be higher than in the surrounding abyssal plains, supporting denser populations of life than previously imagined. The Haddle Zone also hosts populations of xenophyophores, enormous single-celled organisms that can reach sizes of 10 centimeters or more, visible to the naked eye and thriving in the very conditions that would seem most hostile to life. These ancient protists construct elaborate shells from sediment particles, creating structures that resemble miniature works of art scattered across the trench floor. Their presence, discovered only in recent decades, fundamentally altered scientific understanding of what is possible at these depths. Exploration of the Haddle Zone began in earnest during the mid-20th century, and each successive mission has revealed new species and new surprises. The earliest dives relied on bathyscaphs, heavy deep-sea vessels that descended and ascended without propulsion, carrying small crews into the abyss. The first of these historic descents to the very bottom of the Challenger deep occurred in 1960, when two men reached a depth of nearly 11 kilometers, a feat not repeated for over 50 years. Later expeditions have used advanced remotely operated vehicles and high-tech submersibles to continue the exploration, revealing not only the snailfish and the amphipods, but a strange menagerie of life forms adapted to the ultimate extreme of planetary habitability. These creatures of the Haddle Zone, cut off from the rhythms of surface life, have evolved in isolation for millions of years. Each trench may harbor species found nowhere else on Earth, endemic populations that evolved in the absolute geographic isolation imposed by the trench's extreme depth. Scientists suspect that every trench supports its own unique ecosystem, a hidden biodiversity waiting to be surveyed. According to biologists who study haddo communities, less than 5% of the trenches have been adequately explored, and new expeditions consistently discover that their assumptions about the limits of life, both above and below, remain incomplete. Even now, at the very bottom of the planet's deepest wound, the reach of human activity is evident. Amphipods retrieved from the Mariana Trench have been found with microplastic fibers in their stomachs. Call signs of industrial pollution have been discovered in the sediment of other trenches. The Haddle Zone, once regarded as the last pristine wilderness on Earth, is proving to be profoundly affected by human influence at its very depths. The first human eyes to witness the bottom of the trench belong to two men whose names remain etched in exploration history. Their story, a tale of cold, danger, and near catastrophe waits just below the silent surface of Challenger Deep. This final, farthest frontier of the Hadal Zone, the absolute deepest point, carries a geopolitical name, a geological mystery, and an environmental caution that has implications for the entire planet. Within its depths, in a single whisper, a sound, a stray garbage bag, and evidence of human presence intertwine with sightings of creatures once thought impossible, sealing the enduring mystery of Earth's most hostile yet living territory. A single plastic bag, bleached and tattered, drifting lazily through 8,000 meters of crushing darkness, may be the most unsettling sight ever captured on deep-sea camera. When researchers first reviewed footage from the Mariana Trench in 2018 and saw this unmistakable artifact of human consumption resting on the seafloor, they confronted a truth that defied comfortable belief. The most remote place on Earth, a chasm so deep that sunlight has never touched its floor, had been reached by human pollution before it was reached by human eyes. This discovery, alongside the traces of industrial chemicals found in the tissues of Hadal amphipods, forced a sobering realization. No corner of the planet, no matter how inaccessible, remains untouched by human activity. But to understand how we arrived at this moment, both as a species capable of plumbing the abyss and as one careless enough to contaminate it, one must turn back to a cold January morning in 1960, when two men in a steel sphere descended into history. The Bathyscaphe Trieste, a design conceived by Swiss scientist Auguste Piccard, was less a submarine than a deep-sea balloon. Its heavy steel cabin, a sphere just over 2 meters in diameter, hung beneath a massive float filled with gasoline, which is lighter than water and nearly incompressible. On January 23, 1960, the Trieste carried two men, Swiss oceanographer Jacques Piccard, son of the designer, and United States Navy Lieutenant Don Walsh, on a descent to the bottom of the Challenger Deep. The journey took nearly 5 hours, a slow, steady plunge through waters that grew darker and colder with every meter. At approximately 9,000 meters, a thick plexiglass window in the entrance hatch cracked under the immense pressure, sending tremors through the entire sphere. The two men, cramped in a cabin barely large enough to stand in, faced the very real possibility that the next crack would shatter their only barrier against instant death. They chose to continue. At 1:06 in the afternoon, the Trieste settled onto a soft, diatomaceous ooze at a depth of approximately 10,916 meters. Walsh later described the sensation as landing on a cushion of silt, a gentle arrival after a voyage that had taken them deeper than any humans had ever traveled. Through the small porthole, illuminated by the Bathyscaphe searchlight, they observed a flat, desolate plain. And, unexpectedly, a fish, not a shapeless, eyeless creature of science fiction, but a flatfish, resembling a soul lying on the sediment. Its presence generated immediate controversy. Some ichthyologists argued that no fish could survive at such pressure, while others cited the observation as proof of life's tenacity. Decades later, when the Hadal snailfish was formally documented at similar depths, the Trieste sighting gained renewed credibility. The two men remained on the bottom for only 20 minutes before beginning their ascent, and it would be 52 years before another human returned. That return came in dramatic fashion on March 26, 2012, when filmmaker and explorer James Cameron piloted the submersible Deep-Sea Challenger to the bottom of the Challenger Deep. Cameron's vessel, a vertical torpedo, designed for a single occupant, descended in just under 2.5 hours. He spent approximately 3 hours on the seafloor, collecting samples and filming what he described as a desolate but beautiful landscape. The submersible suffered a series of technical failures during the dive, including the loss of its starboard thruster and a hydraulic fluid leak, but Cameron completed his mission before returning safely to the surface. His solo expedition, conducted in partnership with National Geographic and the Challenger Deep mission team, collected geological and biological samples that continue to inform scientific research. Cameron's dive proved that newer, more agile submersible technologies could replace the massive bathyscaphes of an earlier era, opening the door for more frequent exploration of the Hadal Zone. The decades between the Trieste and Deep-Sea Challenger dives were not empty of exploration. Unmanned vehicles, far more cost-effective than crewed submersibles, were deployed by research institutions from Japan, China, and the United Kingdom. These remotely operated and autonomous vehicles surveyed trench ecosystems across the Pacific, from the Japan Trench to the Kermadec Trench, discovering species at depths previously considered impossible. Among the most significant findings were the Hadal snailfish populations observed at depths between 6,000 and 8,000 meters in the Mariana and Japan trenches. These fish, filmed by deep-sea cameras, displayed behaviors never before witnessed, hovering motionless above the sediment, feeding on amphipods, and navigating the darkness with small, pressure-adapted eyes. Each expedition added new species to the catalog of Hadal life. The amphipods retrieved from trench floors revealed not only adaptations to pressure, but disturbing traces of human activity. Further analysis of the tiny crustaceans showed contamination from persistent organic pollutants, chemical compounds banned decades ago but still circulating through the global environment. The trenches, it turns out, act not only as funnels for organic matter, but as final resting places for the chemical residues of industrial civilization. Currents carry surface pollution into the deep, where it settles onto the abyssal plains and descends into the Hadal Zone. The plastic bag filmed in 2018 was proof enough, but the chemical contamination told a subtler and more alarming story. The United Nations Environment Program has documented plastic debris in every ocean trench surveyed, at depths ranging from the Java Trench to the South Sandwich Trench. One research group estimated that over 200,000 cargo containers are lost at sea each year, leaking their contents into the water. Much of this debris eventually sinks or breaks apart into microplastics, which infiltrate the food chain at every level. The amphipods of the Mariana Trench, creatures that have evolved in isolation for millions of years, now carry within their tissues the fingerprint of a species they have never encountered. This is not merely a symbolic tragedy. It is a biological contamination that may affect the health, reproduction, and survival of deep-sea organisms already living at the very edge of biological possibility. Scientists studying the Hadal Zone have documented over 400 species that rely on the trench environment in muth one way or another. The unique geology of each trench, combined with the extreme pressure and the isolation of the depths, has produced endemic species found nowhere else on Earth. The loss of even a single species would represent an irreversible chapter in Earth's evolutionary history. Yet the primary threat to these ecosystems may not be pollution alone, but a more direct form of exploitation currently being considered by the global mining industry. Deep-sea mining, which targets polymetallic nodules rich in manganese, nickel, and rare earth elements, is being planned for abyssal plains and potentially for trench slopes. These activities could destroy habitats before they have been adequately studied and could release plumes of sediment that smother surrounding ecosystems. Documents from the International Seabed Authority indicate that contracts for deep-sea mineral exploration currently cover over 1.5 million square kilometers of the ocean floor. The Hadal Trenches, located mostly within exclusive economic zones of Pacific nations, are not immune from this activity. As the demand for electric vehicle batteries and renewable energy storage grows, the pressure to extract these resources is intensifying. The scientific community has called for a moratorium on deep-sea mining until comprehensive environmental impact assessments can be completed. But the geopolitical and industrial forces at play are powerful and persistent. The exploration of the Hadal Zone has thus entered a new chapter. The question is no longer simply what lies at the bottom of the trenches, but how humanity will choose to interact with these last frontiers. The same technological advances that enabled the Trieste and Deep-Sea Challenger dives now enable remote observation, sample collection, and environmental monitoring. Every new mission returns evidence of life persisting against all odds, along with evidence of human reach eroding the isolation of these pristine ecosystems. During the 2012 dive, Cameron reported seeing an abundance of small scavenging animals, but also patches of the seafloor that appeared disturbed. He noted that the sediment at Challenger Deep seemed more heavily impacted than expected, an observation attributed to currents and the topography of the trench. The image that lingered in his mind, however, was not of the creatures but of the plastic debris he encountered, a reminder that no depth on Earth is beyond influence. The descent has now reached its ultimate conclusion. The deepest point of the seafloor waits with its broken dreams of total isolation, its fragile survivors, and its accumulating evidence of planetary interconnection. What happens in the final bowels of the Mariana Trench shapes the conversation about deep-sea conservation, the limits of exploitation, and the responsibility of the species that, however indirectly, has touched every part of Earth's surface. The story of the Hadal Zone is not finished. Its final chapters, still being written, will determine whether the last wilderness on Earth remains a sanctuary or becomes proof of humanity's failure to protect even its most unreachable places. The Mariana Trench is deeper than Mount Everest is tall. This simple comparison, often repeated, barely hints at the scale of what lies beneath the Western Pacific. Mount Everest rises 29,000 feet above sea level. Challenger Deep, the trench's deepest section, plunges approximately 36,000 feet below the surface. The summit of the world's tallest mountain, if placed at the bottom of this abyss, would still find itself submerged beneath more than a mile of crushing, sunless water. But even this dramatic comparison fails to capture the full strangeness of a place where liquid sulfur pools on the seafloor, where mud volcanoes spew almost pure carbon dioxide, and where pressure reaches over 8 tons per square inch, an environment so extreme that some scientists argue it is more hostile to life than the surface of Mars. The Mariana Trench stretches for over 2,000 plus, 500 kilometers in a gentle arc east of the Philippines, carving a wound in the Earth's crust so vast that it measures 120 times larger than the Grand Canyon. Within its boundaries lie millions of acres that remain virtually unknown to human eyes. The trench is not a single uniform chasm, but a complex geological system shaped over tens of millions of years by the slow, grinding collision of two immense tectonic plates. To understand how this abyss formed and why it holds conditions found nowhere else on the planet, one must first travel back to the very dawn of the Pacific Ocean itself. The story begins during the age of the dinosaurs, when the Pacific Plate began its slow, inexorable march westward. This colossal slab of oceanic crust, forged at mid-ocean ridges where molten rock rises from the Earth's mantle, has been moving at a rate of several centimeters per year, roughly the speed at which fingernails grow. For over 180 million years, it has traveled across the Pacific Basin, carrying ancient seafloor toward the edge of Asia, where it meets the Mariana Plate, a smaller and denser crustal fragment. The Pacific Plate does something remarkable. It dives beneath its neighbor, plunging down into the Earth's mantle in a process known as subduction. This descent of oceanic crust into the planet's interior has carved the trench as surely as a say. Plow cuts through soil, the leading edge of the Pacific Plate, dragged downward by the immense weight of the slab above, has created a deep, V-shaped gash in the seafloor that extends to depths where the pressure would crush any surface structure within milliseconds. The exact depth of Challenger Deep has been measured repeatedly over the past century, with each new expedition refining the numbers. The most recent surveys, conducted using state-of-the-art multi-beam sonar and pressure sensors, place the deepest point at approximately 36,070 feet, just under 11,000 meters. At this depth, the weight of the water column above exerts a force of roughly 8 tons per square inch, equivalent to the weight of 50 fully loaded jumbo jets pressing down on a single square meter of surface. The violence that created this trench has not ceased. Subduction zones are among the most geologically active places on Earth, and the Mariana Trench lies within the infamous Pacific Ring of Fire. a horseshoe of volcanic arcs and earthquake epicenters that encircles the entire ocean basin. Along the same boundary, where the Pacific Plate descends, the Mariana Islands rise from the depths, a chain of volcanic peaks born from the melting of the subducting slab. These islands, named for Spanish Queen Mariana of Austria in the 17th century, form the crest of a massive volcanoes and include some of the most active volcanoes on the planet. Below the waves, this same geological fury has created a landscape unlike any other on Earth. Thousands of hydrothermal vents, mud volcanoes, and pools of liquid sulfur scattered across the trench walls and floor. The Challenger Deep itself, named for the British research vessel HMS Challenger, that first sounded its depths in 1875, sits at the Turn Emenselv, southern end of the Mariana Trench in the Pacific Ocean, near the island of Guam. The British survey ship, using simple weighted lines, recorded a depth of over 8,000 meters, an astonishing reading for the era, though modern sonar would later reveal the true depth was far greater. After multiple subsequent surveys and expeditions, it is now believed that the Challenger Deep consists not of a single point, but of a small basin, approximately 7 kilometers long and 3 kilometers wide, with the deepest spot varying by as much as several hundred meters, depending on the measurement technique. Conditions at the bottom of this basin are almost beyond human comprehension. The temperature hovers within a few degrees of freezing, just above 0 degrees Celsius, though hydrothermal vents in the surrounding trench walls can heat localized waters to hundreds of degrees in their immediate vicinity. Sunlight has never penetrated to these depths. The photic zone, where light can support photosynthesis, extends only to a maximum of about 200 meters. The Haddle Zone, the deepest layer of the ocean, begins at 6,000 meters and continues downward, a realm of perpetual darkness, spaced light years from the evidence of any sunrise. The pressure at these depths has consequences that extend beyond simple crushing force. At 8 tons per square inch, the structure of water itself changes. Seawater at Challenger Deep is markedly denser than at the surface. Compressed by the immense weight of the column above, gases that would be buoyant at surface pressure dissolve or crystallize. The membrane of any organism that had not evolved specifically for these conditions would collapse instantly as its internal fluids equalized with the surrounding pressure, destroying all cellular integrity. Yet life not only survives in this environment, it thrives, populated by extremophilic microbes that have adapted to extract chemical energy from the minerals leaking from the ancient crust below. According to the National Oceanic and Atmospheric Administration, NOAA, the trench is home to geological features that produce phenomena unheard of anywhere else on the planet. One mud volcano in the region produces almost pure liquid carbon dioxide, a bizarre effluence that pools in the sediment and supports populations of bacteria capable of metabolizing this normally toxic compound. Another vent basin hosts a pool of liquid sulfur, molten yellow minerals seeping from the Earth's interior, forming lakes of sulfur where few multicellular organisms can survive. In other areas of the trench system, Hydrothermal vents spill out water so acidic it approaches battery acid, yet some extremophilic species exclusively survive on bacteria harvested from these scalding, chemically violent streams. These hostile conditions have not gone unnoticed by the scientific community. In 2009, the same day, January 16th, that the Marianas Trench Marine National Monument was established. The Mariana Trench and Mariana Arc of Fire National Wildlife Refuges were also created. The combined designations now protect portions of this tremendously complex natural world, a conservation record that scientists argue is only beginning to yield its deepest secrets. The monument preserves one coral reef ecosystem that hosts the highest density of sharks anywhere in the Pacific, as well as another zone with some of the most diverse collections of stony coral known to science. The descent to this dark, oppressive underworld is a journey that begins quietly enough. Above the trench axis, sunlit surface waters teem with life. Schools of skipping fish, patrolling sea turtles, swarming plankton. Within the first 200 meters, light dwindles to a blue glow. Deeper still, the glow fades to absolute black. What lies on the floor of this fractured abyss is a world shaped by volcanic violence, freezing temperatures, and crushing pressure. And yet, even here, discovery has shown that these extreme conditions, while deadly to most surface life, may be just the environment needed to reveal where biology meets geology in the closest embrace possible. A single-celled organism, larger than the palm of a human hand, encased in a shell of its own making, sits motionless on the sediment of Challenger Deep, nearly 11 kilometers below the ocean's surface. This creature, a xenophyophore, belongs to a group that scientists once believed could not exist at such crushing depths, yet here it thrives, constructing delicate, artful structures from the mud around it. For decades, the scientific community regarded the deepest trenches as sterile wastelands where pressure made life impossible. The discovery of these enormous single-celled beings, alongside vibrant microbial communities that thrive in absolute darkness with no sunlight and no organic rain from above, fundamentally rewritten every assumption about the limits of life on Earth. And it is precisely this fragile, newly revealed world that now faces a threat far more immediate than crushing pressure. The rumble of industrial machinery descending to harvest minerals from the abyssal floor. The first comprehensive mapping of the Mariana Trench in recent years employed instruments of astonishing sensitivity. In 2012, researchers from Washington University in St. Louis and the Woods Hole Oceanographic Institution conducted a mother's seismic survey to investigate the subsurface water cycle, using ocean bottom seismometers and hydrophones to map structures as deep as 97 kilometers, over 60 miles beneath the seafloor. Their work revealed a hidden plumbing system connecting the ocean to the Earth's interior, water cycling through fractures in the subducting plate and influencing volcanic activity along the entire Mariana Arc. But these structural revelations were accompanied by biological ones of equal magnitude. Within the sediments collected from Challenger Deep, microbiologists identified thriving communities of microbes that rely not on photosynthesis but on chemosynthesis, extracting energy from inorganic compounds like hydrogen, methane, and sulfur seeping from the Earth's interior. These microbial ecosystems exist in a kind of geological chemistry set, independent of the sunlit world, and served as the inspiration for astrobiologists searching for life on Europa and Enceladus, moons with subsurface oceans and hydrothermal activity that may resemble the conditions of the deepest trenches. The xenophyophores, which can reach sizes of several centimeters, represented something even more unexpected. These giant single-celled organisms accumulate particles of sediment to build their intricate shells, agglutinated tests that resemble delicate works of ceramic art. Scientists found them scattered across trench slopes, sometimes in densities that suggested robust, thriving populations. Their existence at such depths offers a lesson about the incredible adaptive capacity of life, but also raises urgent questions about the impact of human activities on these ancient, slow-growing organisms. Studies estimate that some deep-sea species may take centuries to reach maturity. Their low metabolic rates and sparse food supplies making recovery from damage essentially impossible on human timescales. The same year, the seismic survey mapped the trench. Explorers returned to the deepest point with new eyes. James Cameron's 2012 solo dive to the Challenger Deep collected sediment samples that revealed surprising biodiversity represented by small crustaceans, amphipods, and the sea cucumber species found nowhere else on Earth. The samples contained both new species and traces of man-made chemicals, including polychlorinated biphenyls and polybrominated diphenyl ethers, compounds banned decades ago, yet still circulating through the global environment. The trenches, it turns out, act as final sediment traps. The organic carbon that accumulates there, along with any contaminants attached to sinking particles, becomes locked into the seafloor, where slow-moving currents diffuse them over vast regions of the deep. This was the first hard evidence that human pollution reaches even the most remote oceanic zones. The fragility of these ecosystems has taken on new urgency in recent years due to the rise of the deep-sea mining industry. The abyssal plains surrounding the Mariana Trench contain significant deposits of polymetallic nodules, potato-sized rocks rich in manganese, nickel, copper, nickel, and rare earth elements indispensable for manufacturing electric vehicle batteries, wind turbines, and smartphone screens. Several corporations have filed exploration contracts with the International Seabed Authority covering over 1.5 million square kilometers of ocean floor. While commercial mining has not yet begun, the technology is being developed and tested. The potential destruction from these operations is staggering. Mining vehicles would traverse the abyssal plains, excavating the sediment and crushing every organism in their path. Plumes of disturbed sediment could drift for kilometers, smothering surrounding ecosystems, while the removal of polymeralic nodules would destroy habitats that require millennia to regenerate. The Hadal trenches themselves, unlike the flat abyssal plains, lie mostly within exclusive economic zones of Pacific nations, including the United States around Guam Japan, and Pacific Island states. Some of these nations have established marine protected areas, including the Marianas Trench Marine National Monument, established in 2009, which currently shields substantial portions of the trench from exploitation. Yet the monument's protections face continuous pressure from fishing, ship traffic, and potential mineral extraction industries. A report from a consortium of deep-sea scientists concluded that mining activities in such environments could wipe out endemic species whose entire global population is confined to a single trench basin. Because Haddle species are uniquely adapted to each trench's specific chemistry, temperature, and depth profile, their extinction would constitute an irreversible loss to evolutionary history. Protecting these ecosystems demands a genuinely holistic approach. The scientists studying the Mariana Trench recognize that its treasures include not only the visible marine life of its upper reaches, the shark-dense coral reefs, and diverse stony corals protected by the marine monument, but also the unseen microbial and single-celled communities in its deepest recesses. They propose that any future development must be preceded by thorough, baseline ecological surveys and long-term monitoring programs, with complete prohibitions on mining in the most ecologically sensitive zones. For every new technology brought to bear on the abyssal depths, new species emerge. In one expedition, bright pink snailfish were observed, feeding on swarms of amphipods near a hydrothermal vent. A species of pale, translucent octopus was captured on film for the first time, hovering on delicate paired fins, like a ghost of the deep. Another rover, launched from the NOAA ship Okeanos Explorer, was able to reach just halfway into the Mariana Trench before its cameras revealed the stunning diversity of life they encountered on the trench's upper slopes. Basket stars with coiled endings, Crinidea with feather-like arms, bamboo corals hosting purple brittle stars, chimeras with reflective eyes gliding past, vent chimneys coated with microbial mats and surrounded by crustaceans. The loop opens wide now. As the industrial world encounters the deep sea, these pristine ecosystems face existential threats. The deep-sea mining debate has become a flashpoint in broader discussions about sustainable resource use and the preservation of the planet's last unexplored frontier. The relatively low resolution of current ecological data, the slow growth and endemic nature of deep-sea species, and the irreversibility of mining damage all strongly suggest that halting regulation should be more urgent than encouraging development. What happens in the Mariana Trench in the coming decades will set a precedent for every other deep-sea region. Whether humanity treats the ocean's depths as a sacred heritage or a bottomless mine, the abyss is not mute. It speaks through the millions of species that call it home, through them and their silent, watchful waiting. Less than 5% of the ocean has been seen by human eyes, yet every one of its creatures carries a memory of the surface, even those that have never tasted sunlight. The deep sea, in its crushing darkness and patient cold, remains tethered to the bright world above through an invisible thread of falling particles, migrating bodies, and chemical bonds that connect the smallest microbe to the largest whale. As the journey ascends, each layer of the ocean reveals itself not as a separate realm, but as a single, unified system, a living archive of Earth's history, and a frontier of discovery that still holds more questions than answers. The ascent from the Hadal zone is not a simple reversal of the descent. It is a gradual reacquaintance with light, warmth, and life, a passage through realms that are at once familiar and forever changed by the knowledge gained in their depths. The water warms by fractions of degrees as the vessel rises past 8,000 meters, past the snailfish that hover at the very edge of vertebrate possibility, past the amphipods that swarm around, falling carcasses like silent vultures of the deep. At 6,000 meters, the trench walls begin to slope upward, the crushing pressure easing its iron grip. At 4,000, the abyssal plains spread out in their vast monotony, sea cucumbers and brittle stars continuing their slow, patient labor of filtering the sediment. The midnight zone, with its anglerfish and vampire squid, gives way to the twilight realm, where the first faint glimmer of blue light penetrates the darkness, and creatures rise and fall in their eternal, daily migration. Then, at last, the sunlit surface breaks, and the explorer, blinking in the sudden brightness, understands with fresh clarity that the deep ocean is not a separate world, but the hidden heart of the one we inhabit. This interconnectedness is the central revelation of the journey. The phytoplankton of the surface zone, invisible to the journey, naked eye, produce more than half of the oxygen that sustains every animal on land. The twilight zone's nightly migration transports billions of tons of carbon into the deep, sequestering carbon dioxide from the atmosphere and regulating planetary climate. The marine snow that falls through the water column feeds the creatures of the midnight zone and the abyssal plains, while abyssal currents carry oxygen and nutrients to the farthest reaches of the ocean floor. Even the Hadal trenches, the most isolated environments on Earth, receive a steady rain of organic matter from above, and troublingly, an equally steady rain of human pollution. Microplastics have been found in the stomachs of amphipods, collected from the Mariana Trench. Persistent organic pollutants contaminate the tissues of deep-sea fish. A plastic bag, bleached by decades in the water, was filmed resting on the sediment nearly 11 kilometers below the surface. There is no part of the ocean that does not feel the influence of humanity, just as there is no part of the ocean that does not influence the fate of humanity. The deep ocean remains a frontier urgently in need of scientific discovery. Scientists estimate that over 90% of marine species remain undescribed, perhaps millions of species yet to be catalogued, many of them living at depths that have never been explored. The Hadal Zone alone, spanning roughly 45% of the ocean's total depth range, has been sampled at only a tiny fraction of its extent. Every expedition to the deep returns with new species, new behaviors, and new insights into the limits of life. The discovery of hydrothermal vents in 1977 upended the assumption that all ecosystems depended on sunlight. the observation of chemosynthetic communities around black smokers revealed a second, independent tree of life, sustained by chemical energy from Earth's interior. The identification of Haddle snailfish at depths beyond 8,000 meters expanded the known range of vertebrate life. The isolation of microbes from trench sediments that can survive extreme pressure, cold, and darkness has informed the search for life beyond Earth. On ocean moons like Europa and Enceladus, where similar conditions may exist. Each of these discoveries was made possible by a commitment to exploration, a willingness to descend into the unknown and return with knowledge. Yet exploration is not a neutral act. The technologies that enable humans to reach the deep sea also enable them to exploit it. Deep sea mining operations, targeting polymetallic nodules rich in manganese, nickel, and rare earth elements, have been proposed for abyssal plains across the Pacific. Fishing fleets, having depleted surface stocks, are increasingly looking to the twilight zone for new harvests. Climate change is altering ocean temperatures, acidifying surface waters, and disrupting the currents that distribute nutrients worldwide. The very same connections that make the ocean a single system mean that pressures at the surface transmit to the deep. Coral bleaching events in sunlit reefs affect the quantity of marine snow that falls to the abyssal plains. Warming surface waters reduce oxygen concentrations, creating expanding dead zones that may eventually extend into deeper layers. Acidification weakens the shells of pteropods and other plankton, which form the base of the twilight zone food web. The deep ocean, once considered immune to human disturbance, is now understood to be as vulnerable as any other ecosystem. Perhaps more so, because its species grow slowly, reproduce sparingly, and cannot recover from damage on timescales shorter than centuries. This responsibility is not abstract, but concrete. Unlike terrestrial ecosystems, where species can migrate in response to changing conditions, deep-sea habitats are fixed in place. A seamount community, a vent field, a trench slope. Each is an island in the darkness, with no corridor to the next. If a mining operation destroys one vent field, its endemic tube worms and shrimp are gone, not just from that site, but from the world. If a fishing fleet targets lanternfish in one region, the defaunation affects the entire twilight zone whalefall ecosystem and the carbon pump that moderates global climate. The choices made in the coming years about mining regulations, fisheries quotas, emissions reductions, and marine protected areas will determine the fate of the deep ocean for generations to come. Those choices are not hypothetical. They are being made now in policy rooms and corporate boardrooms, in parliamentary debates and international negotiations. The deep sea may be distant, but its fate lies in immediate human hands, and yet the final note of this journey is one of wonder, not merely warning. The history of ocean exploration is a history of impossibility, refuted again and again. The abyssal plain was described as lifeless until the 1960s, when sea cucumbers were photographed laboring through the mud. The midnight zone was considered a biological desert until echolocation and photophores revealed a teeming glowing community. The Hadal zone was believed to be sterile until the Trias descended and spotted a flatfish, and the Mariana Trench, the deepest point on Earth, was found to host xenophyophores, snailfish, and any number of creatures awaiting formal description. 6 centuries from now, when the archives of the deep ocean are fully appreciated, it seems inevitable that the 21st century will be seen as the golden era of ocean exploration, a brief window in which the last undiscovered realms of our planet were opened to human perception. The act of discovery is one of intimacy, a dimming of the unknown as it enters the field of familiar comprehension. What remains beyond the reach of our cameras and submersibles still awaits its testimony. So the submarine surfaces. The water turns from black to blue to brilliant, shining argent light. Hatches open, and the explorer steps into the open air, feeling the warmth of the sun on skin for the first time in many hours. The journey is complete, yet it is only a beginning. For every trench mapped, a deeper seam remains. For every species identified, a new observation reveals unexpected behavior. For every despairing measure of pollution, a discovery shines light on a species that continues to endure. The ocean, in all its depth and mystery, remains the last great unknown on our planet, a vast, living library of creation, waiting patiently beneath the surface for the next brave descent.